Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. This involves collaboration between the universities of Bergen, Oslo, Tromsø, and NTNU, and working with Sigma 2 to manage the national e-infrastructure. In this video, we will provide more details on executing jobs on Fram. In our previous videos, we concentrated on performance testing for different parallel computing methods for matrix multiplication using a Fortran program. During these tests, we utilized some Python testing scripts. Once the testing phase is complete, you'll schedule your computation code as a production job. We'll offer some suggestions on how to structure a job script for this purpose, but please note that these are merely suggestions. After logging into Fram, you'll notice that I've landed on the Login To node. Let's navigate to the OpenMP on Fram directory located in the Work folder using the cd command. Observe how the command prompt changes when you execute this command. By using the ll command, we can view the contents of this directory. You've seen the Fortran program that uses OpenMP before, but let's take another look at it. We note that it uses a matrix dimension of 16,384. The matrices are initialized with values through an initialization loop, where you can observe the OpenMP directives. The matrix multiplication is carried out by a triple nested loop, and again, note the OpenMP directives. The Fortran program concludes with the option to write the C matrix values to a data file. We've named the job script to match the Fortran program, with the difference being that the script has an SH extension and the Fortran program has an F90 extension. This naming choice reflects that the job script is responsible for executing the Fortran program. However, this is merely a suggestion, and you can adopt any naming convention you prefer. Let's examine this job script using the Emacs editor. The job script begins by assigning names for the job and the Slurm output file. Following this, we specify the computational resources required for the job. We request a single node with a single task because the Fortran program uses a pure multi-threading method with shared memory for parallel computing, utilizing OpenMP. The Fram Linux cluster has 32 CPU cores per node. We request to use all cores for our task. We set the wall time to 30 minutes, which allows us to wait in the development queue. For a production job, we typically need a longer wall time, which means waiting in the normal queue. In this situation, we don't use the Quality of Service QoS option. Regardless of the queue, we must provide the account number. The script variable file contains the name for both the script and the Fortran program, and this variable is used later in the script. The recommended error handling environment is applied. We also need to load the Intel Fortran compiler. Note that we are not using the alias Intel defined in the bash rc file. This is because we don't want our job script to depend on any specific configurations from the bash rc file in the home directory. The Fortran program uses OpenMP for parallel computing, so we are setting some OpenMP variables. You might recall that during performance testing, we used these variables directly in the execution command. However, here we are setting them as environment variables. The number of threads is set to match the number of CPU cores per task by using a slurm variable that retrieves this number from the computational resources specified in the script. Additionally, we are applying the OpenMP affinity settings cause and close. The script compiles the Fortran program to ensure it is built on the same type of compute nodes where it will execute. We use the Intel compiler and the script variable file, which contains the name of the Fortran program. The resulting executable from the compilation process is named mxm.exe. We've added script variables to calculate the compilation duration, and this time is logged in the slurm output file. This measurement is optional, so you can choose whether to include it in your script. The executable is launched on the computational resources specified for the job. The time taken for the parallel computing is recorded using similar script variables, and you can decide whether to include this in your script. The script proceeds by using several slurm variables. You've seen the variable that provides the path from which the job script was launched. The script also uses variables that gather information from the specified computational resources. Finally, the job script reports the CPU billing using a slurm variable that provides the job number. Note that we are not using the alias CPU bill defined in the bash RC file. This is because we want to avoid making the job script dependent on any specific configurations from the bash RC file. It is recommended to use aliases from the bash RC file only at the command prompt and not in the job script. At the end, the job script copies the Fortran program and the job script to new files, appending the job number to their original names. The script concludes with the exit 0 command, indicating that an exit status of 0 signifies the job has been successfully executed. We submit the job script to the slurm queue system using the sbatch command. The job is assigned number 5987974. By using the sq command, we can track this job. The job has the specified name and has been active for 7 seconds on the C54 node. Later, another sq command confirms that the job has completed. The job script generates a slurm output file, but let's first clear the terminal. We can verify this by using the ll command, which shows that the file ending with txt has been created. Note that we have renamed the slurm output file in your job script to OpenMP on Fram N16384. You can also see that copies of both the job script and the Fortran program have been created. You can save these files along with the slurm output file to document which versions of the Fortran program and job script were used when executing this job. Let's open this slurm file using the Emacs editor. Remember to use the tab key for autocomplete while typing these long file names. The file first indicates when the job started and on which node it was executed. We can see that the compilation time was about 9 seconds, and the execution time was nearly the same for a matrix dimension of 16,384. The job was submitted from the work folder. The specified computational resources are listed, showing that a single node with a single task using 32 CPU cores was requested. The CPU billing section shows that the billing factor was 32, which matches the number of CPU cores on one node. It also indicates that 59 gigabytes of memory are available on a single node. The job consumed 0.2 CPU hours from the project account. The file shows that the job waited 0 seconds in the queue. Although the requested wall time was 30 minutes, the job had a wall time of 21 seconds. The consumed CPU hours are calculated as 21 seconds times 32 CPU cores, resulting in approximately 0.2 CPU hours. The computation was a single task on 32 CPU cores, with a CPU utilization of about 44%. The exit status was 0, indicating the job was successful. The used CPU time was 4.9 CPU minutes, and the unused CPU time was 6.3 CPU minutes, resulting in a CPU efficiency of about 44%. The low CPU efficiency occurred because only one core was used during compilation, leaving the other 31 cores idle until the compiled program was executed. The memory available on a single node is 59 gigabytes, so the Slurm output file indicates that the allocated memory is 59 gigabytes. The memory usage is reported as 0.2 gigabytes, which is much lower than expected, since we know that with a matrix dimension of 16384, the memory usage should be about 6 gigabytes. This discrepancy is because the wall time for this job is short, less than 10 seconds, and the system is unable to capture the correct memory usage. We can verify the job efficiency with the cef command, which stands for Slurm efficiency. The command shows that the CPU efficiency was about 44%, and the memory usage was approximately 219 megabytes. Therefore, the sf command confirms the same numbers as those in the Slurm output file. Let's clear the terminal. We can append the output from the cef command to the Slurm output file by using two greater than signs. Let's check the Slurm output file to see if the cef output was added. The file shows that the cef output was appended at the end, after the memory statistics. We can try with a larger matrix dimension, so let's open the Fortran program with the Emacs editor. Inside the Fortran program, we'll adjust the matrix dimension to 32,768. Let's also make some changes to the job script. In the job script, we'll update the job name and the name of the Slurm output file. We submit the job script to the Slurm queue system using the sbatch command. The job is assigned number 5988029. By using the sq command, we can track this job. The job with the specified name has been computing for 10 seconds on the C54 node. Using the sq command again shows the job has been active for 37 seconds. A subsequent sq command confirms that the job has completed. Let's clear the terminal. The generation of a Slurm output file can be verified using the ll command, which shows that a new file ending with txt has been created. In the job script, the Slurm output file has been renamed to OpenMP on Fram N32768. Additionally, copies of both the job script and the Fortran program have been created. These files can be saved along with the Slurm output file to document which versions of the Fortran program and job script were used for this job. Let's open this Slurm file using the Emacs editor. Remember to use the Tab key for autocomplete while typing these long file names. The compilation time was approximately 9 seconds, and the execution time was nearly 66 seconds for a matrix dimension of 32,768. The CPU utilization was about 85%. The CPU efficiency has improved because the parallel computing wall time increased to about 66 seconds, reducing the ratio of compiling time to executing time. the memory allocation remains at 59 gigabytes, but the memory usage is now around 24 gigabytes. This is expected for a matrix dimension of 32,768, and the system is able to capture the memory usage more accurately due to the longer wall time compared to the matrix dimension of 16,384. Let's exit the slurm output file and clear the terminal. The saf command can be used to verify the data from the slurm file, confirming that the memory usage is about 24 gigabytes. The saf output can be appended to the slurm file as before. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder, Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos. We can copy any of these files to the home folder. In our next video, we will attempt to increase the matrix dimension to 65, 36, and execute this matrix multiplication process as a parallel computation on the Fram Linux cluster using OpenMP. I am looking forward to the next video, wishing you all happy computing in the meantime.